So let's get going here. So week number 3 quiz. Generally, they were good. There was one problem that I would say about a fourth of the students in the class missed. And so when I see something like that, I like to usually bring it up in class. And it dealt with problem number 4. Let me get back there. Sorry. Here's problem number 4. This is what it looks like from a teacher's view. And basically, you just simply needed to find some eigenvectors. And the very first, it was a choose all that apply question, or choose all that are correct. And the very first eigenvector that you see there is what R gives by default. And everyone got that right. Where students were not getting stuff right is that there were 2 other possible eigenvectors. And something I did bring up during the matrix algebra section was that these eigenvectors are not unique. And basically it corresponds to the length of the vector. So by default, R gives a length of 1 for a vector. But for example, the very last vector there, that's exactly the same, but a length of 10. And so that's why that last one was correct. And with the second one there, if you simply multiply by -1, the first one, that's how you get that vector. Is just pointed in a different direction. That's all. Just like a mirror image in terms of direction. So that's why all 3 of those are correct. Again, eigenvectors are not unique. And the way that you can come up with different eigenvectors is just simply multiply the eigenvector by a scalar value. Okay? Any questions about that?
Okay.
Yeah.
Again, is that the last one?
Okay.
How you get that?
Multiply by 10. Multiply. I think, I'm sorry, 5. Excuse me.
I think the basic thing was that it should satisfy that capital A where the capital A into B equal to B into lambda.
Yeah. And so the key is that you can make that B a number of different quantities if you just simply multiply, let's say, the default B given by R, multiplied by some constant. And the equality still holds because you have that B on both sides. Okay. Okay, are there any questions before we begin? I want to talk a little bit about test number 1 as well. Any questions before we talk about test number 1, before we get back into the notes? Okay, so next class period on Tuesday, we will have a large review about the tests. I'll give you more specifics about format and stuff, but I just want to set you up now for success to make sure that you understand what the format's going to look like. I've kind of said much of this before, but it doesn't hurt to say it again. So the purpose of having the test this early in the semester is to give an assessment early so that if you find as though that you didn't do well in the test, you can make adjustments to how you study or how you approach the class. This test is only 5% of your grade. So if you end up not doing well, hey, it's not going to hurt you that much. So that's why I like to do this, especially in a class like this when there's such a large, diverse set of backgrounds. Again, the test is closed book, closed note. You will use the computers that are on your desktop here. So I recommend, if you do have time after class, just log on to the computer, just to make sure you can log on. I mean, it's just your usual login and stuff like that you have on campus. I think it's called the UNLAD account you use, okay? Make sure you can log in, see what's available on the computer. It's RStudio and R. I think last Friday I logged onto these computers just to make sure that they seemed to be fine, and they were, or at least I thought they were. But I do recommend that, obviously, computers can have computer problems during the exam. Fortunately, we do have other extra computers in the classroom, so if you do have computer problems, you can move to another computer. But I also recommend that you do bring a laptop with you in case it comes to you need to use your own laptop because you just can't get the computer to work, okay? Now, while it's closed book, closed note, I have that formulas and functions PDF document on the graded web page of my website. You can use that to help you, because I don't want you to have to memorize formulas or memorize actual R code before the test. And so this can be a quick little reference that you can use to help you out as needed. You will also have access to the R programs on my website as well. And the reason why I allow that is because often when you are programming on your own, what you do is you go back to an old program that you've written, or maybe you've found that somebody else has written. You take code from there, you incorporate it into your own program, and then you make modifications to it. So it kind of simulates that process. Now, there are obviously my course notes on my website. I will take those down before the tests. You're not allowed to use my course notes. You can also use R's built-in help. So like if you need help with like the p-norm function for some reason, you can simply look in R's built-in help for that. You cannot Google or do an internet search for p-norm in a web browser. Can't do that. Okay? But you can use the help that's built into R. The installation of R on these computers is rather minimal. You may need to install a package during the exam. So please review how to do that, obviously. There will be no paper passed out for the exam. You will download a Word document from my website, and you'll put all your answers in that. And most likely what you do to turn that in is that you'll go to the Canvas website for this course, and you will see a place to upload it. Okay? Basically, it's going to be like a regular old Canvas quiz, and you'll have a little button to upload. You click upload, click on the file, and then you submit the quiz. And that way I get the material. I will, to help you out, I write the test, so it's going to be an hour and 15 minutes, but as you might imagine, some students like to have a little bit extra time. And so I will start making the test available at 12:25. So please, if you can get here early, get here 5 minutes early. So you have 5 extra minutes on the test on the front end. And since there's not, I don't think, a class in here after us, I don't mind going a little bit longer. I do know that some of you might have classes after this as well. So it's not like I'm going to give you an extra hour because that wouldn't be fair for those students who have another class after this. But I would imagine at least 10 minutes extra, at least. Okay. And again, we will review during the next class. Are there any questions? Okay. So let's get back to this data distributions and correlation set of notes. We left off on page 26, but just to review a little bit here. We were looking at the multivariate normal distribution, and we looked at a specific case of it where we had a bivariate normal distribution, meaning that we had 2 random variables, x1 and x2. We put those into a vector. We call it x. That's called a random vector. With the multivariate normal distribution, you can fully get at, in terms of the mathematical expression for it, to find probabilities associated with it, which at some point we will. You can fully specify, that's the word I'm looking for, fully specify the normal distribution if you specify what the mean vector is. So in this case, it was 15 and 20. So the mean, or the expected value of x1 is 15. Mu1 is 15. And then also if you specify the covariance matrix. So the covariance matrix, the values on the diagonal, let me get a highlighter out. The values on the diagonal are the corresponding variances for the variables. And then we learned about something called the covariance last time, and these are on the off diagonal. So for row 1, column 2 of that matrix, that's the covariance of x1 and x2. And all that a covariance measures is the association between random variables. Very similar to a correlation, The difference is these covariants, the actual numerical values of the covariances are unbounded, where correlation is always between -1 and +1. Okay, so we use, and also the correlation was, excuse me, the correlation between x1 and x2 was 0.45 for this particular example as well, and we can find that from the covariance matrix. And so then we did a plot, and we had this nice little 3D representation of the bivariate normal distribution that we specified. Notice how it's centered at its corresponding mean. What controls that spread of the distribution out is that covariance matrix. Relate this to a univariate normal distribution cases to help make sense of that. The volume underneath this surface here, underneath down to f of x is equal to 0, that volume is 1. Why? Well, you learned in your first stat course about how you can't have a probability more than 1. And similar to the normal distribution, the univariate normal distribution, we can find probabilities with the bivariate normal distribution as well. Now, at f of x is equal to, let's say, 0.1 here, if we were to, let's say, somehow draw a plane across the plot and hit this green surface, where it hits it corresponds to the x1 and x2 that's equal to f of x equal to 1. And so then we could actually plot that in a contour plot. So I'm going to highlight here. Here's 0.1. Here's the corresponding contour, or the places where x1 and x2, I can keep on drawing, but I'm not drawing very well. The places where x1 and x2, where f of x is equal to 0.1. Okay, so let's now begin something new. Come on, I don't know why my eraser doesn't like to work here. Oh well. Actually, we'll do it this way. Okay. Here's a question for you. This is a little bit later in the notes from where we stopped. If I were to take a sample from a population characterized by this bivariate normal distribution, so I would get x1 and x2. Let's say I took a sample of maybe 100. Where do you think, and then I did a scatter plot, where do you think the majority of those values would fall on this plot here? I plot the x1, x2 pairs. Would you expect any out here? How about here? How about here? Yeah, you would start expecting them more towards the middle. Why? Because that's where the higher probability is. And in fact, if I were to just kind of estimate what it would look like, it would probably look something like this. Where you would have a larger number of them towards the middle, because that's where that bivariate normal distribution is higher. There's more probability there. Okay. Let's see if I can erase that. Now, let's relate this to, let's say, in another class where maybe you had a variable x, you had a variable of y, and you did a scatter plot. Suppose you did a scatter plot and you had something like this. What would the estimated correlation be, do you think, approximately? Close to +1. Now, if I did something like this, would it be higher or lower? Lower. Okay, maybe about 0.5. Now, suppose if I had something like this. What do you think the estimated correlation would be?
0.
About 0. Okay, keep that in the back of your mind. Let's go to these questions then. That this is exactly where we left off. So what would happen to then this contour plot What would happen to the contour plot if, let's say, the mean vector changed? Suppose mu1, instead of being 15, it was 20. What would happen to the contour plot? Would it be exactly where it's at? In terms of, what would happen to the contours? Would they be exactly where they at, or would they move, or would they change shape? Let's relate this to, again, your first stat course. Here's a normal distribution centered at mu. Let's say I add, so suppose I form a new mu. Let's call it mu nu, where it was equal to mu plus 5. What do you think for this different probability distribution, what would happen? Where would it go? It would shift to the right. So you might have something that looks like this, mu plus 5. And I meant to draw it at exactly the same shape, okay? Because the variance is not changing at all. All we would have is its shift. Now, when we look at then the contour plot, oh, come on. If mu1 was equal to 20, what would happen to the contours? They move to your right, okay? The contours remain exactly the same, though. Same shape, because the covariance matrix isn't changing. Suppose sigma 1, 2 is equal to 0. So that means the covariance of x1 and x2 is equal to 0. What does that mean for row 1 and row 2? Sigma 1, 2 is equal to 0. What does that mean for row sub 1, 2, the correlation between variable 1 and variable 2? What would that correlation be?
Also 0.
Also 0, yes. Okay. Now remember this little plot that we did here for an estimated correlation coefficient? Imagine if I were to draw the contours corresponding to a bivariate normal distribution that had exactly the same correlation, exactly the same mean. Those contours would look like this. Okay? Why? Exactly the same reasons as what we saw for that first plot that we looked at, where I had the blue dots. So notice how the contours now would no longer be tilted, they'd be more upright. Why? Well, because we have no association between x1 and x2. That's why. Knowing x1 is not going to help you get x2. And so, just to show you that indeed that happens, in my program here, when we actually plotted the bivariate normal distribution for the first time, where is that? Okay. What you can do is go into the program, and where I have my sigma there, just change that 0.5 to 0, run the code, and let's see what happens. There's the contour plot. Now, are these perfect circles that we see there? Not quite. They are formally ellipses. The reason being is because the variance of x2 is 1.5. The variance of x is 1. So there's more variability in the x2 direction. So if I wanted a perfect circle, what would I need to do? Make sure that those variances were exactly the same. So the variance of x2, suppose we set that equal to 1, then you would get perfect circles. And so let's say that row sub 1, 2 is very, very close to 1 or very, very close to negative 1. What do you think would happen to the contours? remember what we started off with when we were talking about a sample. The contours would become very, very narrow. Because now we have a strong relationship between x1 and x2. So if I know x1, I'm going to have a good idea what x2 is, and vice versa. And so to represent that in a probability context, then and let's actually do a plot so you can see it. Okay, let's see here. So I'm going to make the covariance 0.99. I'm going to make both variances equal to 1. Let me actually close out that. Look at those contours. Here's the 3D plot. Look at that. It's almost essentially, it's really squeezed in. It's almost like you could view this in just 2 dimensions rather than 3. That's going to be an important thing coming up later. Because we will actually take advantage of that for some of our statistical methods that we will eventually develop. So anyway, so this is a nice little demonstration of what the multivariate normal distribution gives you. Obviously, we focus on the bivariate case, but it extends to trivariate, extends to more than 3 dimensions or more than 3 variables as well. It's just obviously easier to show it with just p equal 2. But also what this, I think, hopefully helps you see is how R can be used as a learning tool, not necessarily as a computational tool. Because I'm able to ask questions about what if something changed? Well, let's take a look. I have this nice little program that helps me do that. And hopefully you can take advantage of that with some of my other programs as we go along in this semester. Okay. So we were talking a little bit about taking a sample. So let's formally talk about what multivariate summary statistics are. What would be the estimated mean vector? What would be the estimated covariance matrix if we actually took a sample? So first of all, some notation. I could say my sample is, instead of saying x1, x2 down to xn, now I have a bolded x1, a bolded x2, a bolded xn to represent these are p by 1 vectors. So I'm measuring information on multiple variables at the same time. Often we will say that this sample, we're going to take a random sample from some population where we don't know what the actual probability distribution is that would help us understand that population, but we know that we can calculate it. We know that there's going to be a mean. We know that there's going to be a covariance matrix. So in a formal sense, we could say x sub I, and then in those brackets there, from I equal 1 to capital N, I have a random sample. Comes from a population that has a particular distribution that we don't know, but we know that there's going to be a mean vector, and there's going to be a covariance matrix. We could also shorten it to look like this too if we just realize, okay, I'm always going to take a sample size n. So, what does the estimated mean vector look like? First of all, notation. So notice I have a bolded mu, and I put a little caret sign on top of that, meaning a hat. In statistics, we pronounce that as a hat. So mu hat is my estimated mean vector. And all it is you sum up all the mean vectors, divide each element by n. That's it, what you would expect. You could look at it from this point of view as well, where essentially what we have is the regular old sample mean that you would learn in your first stat course. We have the sample mean for variable 1 as the 1, 1 element, sample mean for variable 2 as a 2, 1 element, and so on. Now, in terms of the covariance matrix, so what you could say is the population covariance matrix, or the true covariance matrix. We've seen that last time. We used the Greek uppercase letter sigma to denote it. And what it is an expected value, where we look at how far is my mean vector from how far is my x vector from the mean vector. If I have p variables, I'm going to get a p by p matrix. Now let's put this now into a sample context. Now I have some actual data. Look what I do here. Very similar. I take each data value that I have, subtract off its corresponding mean vector, do the same thing on this side as well, transpose it. So this part here is going to be p by 1. This part is going to be 1 by p after the transpose. So I'm going to have a p by p matrix. And I'm going to do that for each observation in my sample. That's what the little r then tells me. I sum up each of those p by p matrices, and I take that sum times 1 over n minus 1. Let's relate this to a regular old sample variance that you will learn about in, again, probably your first stat course. You would have used probably notation, something like this. Hopefully that looks familiar there. Okay? Where you take your x's, you're going to observe the x's, subtract off the sample mean denoted by x bar, square it, add them all up, divide by n minus 1. Does anyone know why we divide by n? Well, first of all, essentially what we have here is like an average value. Remember what an expectation means? On average, what happens for the stuff that's inside of it? When we have an actual sample, we're interested in expected values. Well, we sum up the sample values. We then take like an average, like dividing by n. Why is this n minus 1 rather than n? It is related to the degrees of freedom. We lose a degree of freedom because of x bar. But I'm actually looking for a little bit of a different answer. I would expect your instructor would tell you why. If you've taken a mathematical statistics class, you've probably done a proof associated with this for why we do n minus 1 there.
Because in order to get that mean, we can play with all the elements that are part of the mean, but the last one.
Well, I think you're getting at kind of a degrees of freedom argument. I'm actually looking for something else. Why do I take n minus 1 there versus n if I want to find an average value? The word I'm looking for starts with UN. Not as in University of Nebraska, but it starts with UN. Yes. Nope, but thank you for taking a chance. Any other ideas? I'll give you, we could play like a game here. You can name it in how many letters? I'm going to put another letter here. Unbiased, thank you. Okay. Hopefully you've heard of that concept of unbiased. Okay. In a mathematical context, if I think of S squared, my sample variance, as a random variable, not as a computed value, but as a random variable, the expected value of S squared is equal to sigma squared. So when this happens, we refer to the estimator S squared as an unbiased estimator. This seems like a good quantity or quality that you would like to have of any kind of estimator, that the expected value of it will be what you're trying to estimate. So also, the expected value of x bar, if we think of it as a random variable, is the corresponding population mean. If you've done a mathematical statistics course, like 462, 301, 880, you would have, or you should have, actually done the mathematical proof that shows that this is true. So what this means then, though, if I were to instead only divide by 1 over n, if I will only divide by n rather than n minus 1, I do not get an unbiased estimator. And unfortunately, then this new version of my estimator is not going to be as good as if I were to use an unbiased, because it's not going to be equal to sigma squared. So in a similar manner, for my covariance matrix, estimated covariance matrix, we have a 1 over n minus 1 there rather than 1 over n. In terms of notation, to say that this is indeed an estimated covariance matrix, we put a hat on top of sigma. Please be very, very careful when you're doing tests, when you're doing projects, and let's say you might have to actually write out mu hat, sigma, or sigma hat. All 4 of those things are different quantities. So if you meant to say sigma hat, but you put sigma, unfortunately that is wrong and you will lose some points. Okay, so be very, very careful about that. We have a population, we have a sample. You can calculate something in a sample, you can calculate something in a population as well. The sample is going to have the hat on top of it. Okay. So, this is what then the estimated covariance matrix then looks like if we put hats on top of all the little sigmas. And this next set of equations here just looks at this from an individual estimated covariance point of view. Notice, for example, with that estimated variance, I'll just write it out again using the notation that you would see in another class. So this is not our notation, so please be careful. Notice these are essentially equivalent, just different notation. Okay, so we're on page 29. The stuff that I have highlighted in blue here, or outlined in blue, don't worry about that. We might come back to it later. Well, what about then the estimated correlation? We're going to denote that by r sub ij, little r sub ij. That's often what's often used with correlation. So perhaps in another class you use that little or lowercase r as well. The correlation, the estimated correlation matrix, we're going to call it capital R. I guess I could have called it capital P with a hat on top of it. Sorry, I didn't. The notation I'm using here is a notation from one of those books that I referenced in the syllabus. I just decided to keep with their notation. So then what does then the estimated correlation coefficient look like? Well, you use the same expression for as with this in terms of the true or the population correlation coefficient, that rho sub ij, except for you put hats on top of the sigmas. And so based upon what we saw for those expressions, here's the actual correlation. This expression should not really look new. It's just a little bit notation. So we still have that file open. Yeah. So for example, when I teach a Stat 801 course, or this is actually from my Stat 801 class, I use the same, actually for this part, I use pretty much exactly the same for a Stat 380 class. When I've taught a Stat 218 class before, I use the same notation as well. There's the expression that you would have seen in one of those classes for an estimated correlation or a sample correlation coefficient, and is exactly the same as what we have here, just a different notation. I could put all these estimated correlations then into that correlation matrix. So let's do some calculations with the serial data. We're going to let x1 be sugar, x2 be fat, x3 be sodium, and these are going to be adjusted for the number of grams per serving. We talked about last time why that was important. It's because each cereal could potentially have a different serving size. And so we have to adjust for that. So notationally, since I have a sample size of 40, we can say that x sub I from I equal 40 represents a random sample from some population where we don't know what the exact distribution is, but we know that there's going to be a mean vector, there's going to be a covariance matrix. So we could actually go through the math to do the calculations. I'm just going to touch on it here. So for the mean vector, remember Kellogg's Razzle Dazzle Rice Krispies had an adjusted sugar value of 0.3571. The very last cereal, unfortunately I don't remember the name of it, had a value of 0.1 for sugar. Okay, so I add all those adjusted values up for sugar, divide by 40, and I get 0.2894 for the estimated mean for sugar. Do that for fat, do that for sodium. Now, what about the estimated covariance matrix? So, here's the actual expression that we saw. And what you can do is put in what the mu hat vector is. So notice that 0.2894 matches what's up there. And what I actually, in some of this you just need to go through on your own just to make sure you understand it. So for the very first observation, first experimental unit, my x1, that vector will be 0.3571, 0, and 6.071. I take that, keep on going all the way down to x40. Now, on a test, am I going to ask you to do all these calculations like this by hand? No. You will either do them in R, which you'll see how to do shortly, or what I might do, just to make sure that you understand the matrices that are going up here, going around here, is what I could do is actually maybe set up this equation here and say, okay, start filling in the first few observations. Actually type what should go in the correct places. So that will be one way I could assess your understanding of this mathematical equation. Okay, so here's the estimated covariance matrix. Here's the estimated correlation matrix as well. So based upon what you see there, does it look like that these variables are highly correlated to one another? Maybe medium correlation with each other or medium association, or there's very little association at all? What do you think? So remember, this represents variable 1, 2, 3, variable 1, 2, 3. So for example, right here, this would be R sub 1, 3. So do we see lots of association or little? Little. Okay. The strongest amount of correlation was that 0.2397 for sugar and fat. I was a little bit surprised when I first saw this because, again, remember those those kids' cereals. What do you think there's going to be a lot of? Sugar, fat. I mean, going into this without actually going through the calculations or I guess my preconceived perceptions, I would expect a little bit higher. But I think what could be happening is that there are some high-fat cereals out there that have very low sugar, especially if they have like lots of nuts in them, because nuts have a lot of fat. And you might have a healthy cereal that has lots of nuts in it but not much sugar. So that could be somewhat of a cause. Okay, so let's look at how we can do some of this stuff in R. So on my computer, I have a folder called data, where I have this actual data set stored. Serial.csv. Again, it's a comma delimited file. And I'm going to read it into R. There's a number of different ways to do it. My favorite way is to use the read.csv function. And I'm going to put that into an object called serial. So serial gets the results from read.csv. Let me make this bigger. And so if I simply type head serial, I can see there's my serial data set, the first 6 observations. I've said this before, I usually always do this right after I read a data set in R because I want to check, did I read it in right? So I would go back to my data file and just double check. You could do the end of the file as well with the function tail, and you get the last 6 observations. Okay. Now, let's actually take a look at the data again. Here's my serving size. Here's my sugar content. The first thing I need to do is adjust the data for the serving size. So I want to take 10 divided by 28 for each observation. So to do that, I pull sugar underscore G out of that data frame. So just to show you that indeed, there's all my sugar values. I'm going to take a divide by the serving size. And so that if I combine the two, I get these adjusted values. Remember how we saw 0.3571 as that first adjusted value for sugar. But now what I want to do is put then these adjusted values back into my data frame where I just was. So to do that, I say serial $, and I create a new variable called sugar. That's all. So, just like how I can access particular variables in my data frame like this, I can actually create new variables in my data frame by putting it on the left side. So that if I take a head serial, there's my new sugar value you can see there. I'm going to do that with fat and sodium as well. And you can see that indeed I did add it. Okay, so how do I do the estimated covariance matrix? Well, fortunately, there's a function in R called cov. So I say cov, and inside of it, I need only the variables that I want to calculate covariances of. And these variables are in columns 8 through 10. So this 8:10 means 8, 9, 10. And notice how I access part of the data frame. I say serial, left bracket. I want all the rows, so I'm not going to designate any particular rows in there. 8:10 saying I only want the columns, those columns. So if I just highlight that part, there you can see I have just the sugar, fat, and sodium. Let's now find the estimated covariance of that. I'm going to put that into an object called sigma.hat. And here we go. Yes?
For the last 2 tasks, is it okay to use, like, before, like, I remember, like, the dplyr functions, like, is it okay to use mutate and select for that kind of stuff?
If you want to, I don't think it's necessary.
Okay.
That is, going to the tidyverse.
Yeah.
But this is pretty simple.
Yeah.
So, yeah, you could do that. Well, what about the correlation matrix? Well, there happens to be a function called core. If I use it the same way as I did with the cov function, there's my estimated correlation matrix. We saw last time there was a function called cov2core that takes a covariance matrix, converted to a correlation matrix. You could actually do that with sigma.hat as well. Well, what about getting the mean vector? A few different ways to do it. I think the easiest way to do it here is to use a function called call means. COL for column, then means for means. And again, I say I just want to take columns 8 through 10 of serial, put that into an object called mu.hat, and there's my means for my mean vector that I would need. There's other ways to do it. I guess another way that's actually even a little bit more general is to use the apply function. Just out of curiosity, who's used the apply function before? Okay, this is a really cool function because what it allows you to do is apply some other function to either like the rows or the columns of a matrix or of a data frame. So if I say apply, in the first argument, name isn't very interesting. It's just x. This is just simply where you put your data. So I want to apply something to this data. I want to apply it by column. That's what margin equal 2 means. If you look it up in the help, you'll see that margin equal 1 would be by row. And then what do I want to have fun with in terms of what function do I want to use? I want to apply the mean function by column. And this is what we get. Okay, same thing. Very, very useful, that function. Let's see if there was anything else. So you can skip this part right there. Now let's go back to talking about that bivariate normal distribution that we saw before. And, I kind of alluded to, well, what would a sample look like in that particular setting? Well, let's have R actually take a sample from a population characterized by this bivariate normal. At least when I teach an introductory stat course, I do a lot of data simulation, meaning simulating data from a population characterized by a probability distribution, because it helps students understand what does this probability distribution actually represent. Because if I know what the probability distribution is, I know what the population is going to look like. Does my sample look like that? Hopefully it does. If it doesn't, you've done something wrong. So I typically spend a lot of time on it. I think it's pretty standard nowadays to do it, and I hope it is, but I'll give you a little bit of an introduction here. So what I'm going to do first is create my mean vector, create my covariance matrix corresponding to this bivariate normal that we've seen before. I'm also going to set a sample size of 20. So I'm going to take a sample of 20 from a population that can be characterized by this bivariate normal. Let me actually go over here. Here we go. Okay. Oops, don't want 2000 yet. Okay. Now, in the MVT norm package, there is a function called RMV norm. R standing for random, MV for multivariate, norm for normal. And what this function is going to do is simulate data from, again, a population characterized by this normal distribution, where the first argument says, what's your sample size? So for us, that would be a capital N. Next argument, what's your mean vector? Next argument, what's your covariance matrix? I'm going to put all these results into an object called X, and this is what I get. Okay. So my very first observation was 16.24 for X1 and 22.54 for X2. This is my sample. Now let's say if I wanted to do it again. So let's say I just execute that code there. I'm not going to put it into X. Oops. Notice I get a different set of values. 15.0794, 19.11. Suppose I do it again. Just a little bit of a quick thing in case you don't know this. The way that I can quickly cycle through my past code is by using the up and down arrow on my keyboard. So if I do it again, I get a different set of data. Okay, so how can well, sometimes though, I like to actually get the exact same data so I can reproduce my results. And to do that, what would I need to do? Anyone know? Set a seed, yes, exactly. So in random number generation, there are what are called seeds. The seeds help, let's say, the random sample grow. It's where the random sample starts from. That's where the name essentially comes from. And so if I randomly choose some number, let's say 7812, and use set.seed with it, this sets a seed. And what R is going to do is say, okay, when I simulate data with RMV norm, I'm going to use a 7812 in its internal algorithm to do the data simulation. I'm going to use it inside of there. We don't need to get into the exact algorithms that people use for random number generation. But what's going to happen is that no matter how many times I run this, I will always get exactly the same sample. If you set the seed right before you do the random number generation. It's useful, obviously, in a teaching context so that we have exactly the same data that we're talking about. But it's also useful in a number of other situations as well, such as, for example, for research, if you want to have reproducibility of your research. Okay, so there's my data. And so what I can do is find the mu hat vector. I can find the estimated covariance matrix, the estimated correlation matrix, and this is what we get. So remember, mu was 15 and 20. Mu hat here looks pretty close. This is what we would expect. This is a good thing. If that didn't happen, I'd be very worried. What about my covariance matrix? Well, remember, variance of x1 was 1. The estimated variance is 0.93. Pretty close. The variance of x2 was 1.15. The covariance of x1 and x2, I believe, was about 0.46. Again, we're getting values that are quite close. It's only from a sample size of 20, too. So this is good. We're getting what we would expect. Of course, we would like to get a little bit closer. What do you think I could do to get closer?
More samples.
Yeah, take a larger sample size. Try to get as close to that population size as you can. So let's say that I took now a sample size 2,000. Let's see here. Remember, 15 and 20 was the true mu vector. We're very close there. Remember, we had 1 for the variance of x1, 1.15 for the variance of x2. Let me just double check that that was the case. I'm sorry, 1.25. I think I misspoke. Okay. 0.5. I apologize. 0.5 for the covariance. And, sometimes we're not getting closer. Well, there is going to be variation from one sample to the next. Let's actually jack it up. Let's go to 2 million, see if we get even closer. And we do. Okay? If I somehow could take a sample size infinity, I would get exactly what mu is, exactly what sigma is. Again, we have a variety of backgrounds in this class, so sometimes I will ask a question for people who have a certain background, other times a different background. So for those of you who've had a mathematical statistics class, what was this a demonstration of in terms of how we were increasing the sample size and the estimated values were getting closer to the parameter values? What was that a demonstration of? Does anyone know? Not the central limit theorem, but there is, the central limit theorem does use that to some respect. So, it is a convergence of some sort, yes. Anybody heard of the weak law of large numbers before? This is an example of that. Okay? Don't worry about it if you've never heard that before. I'm not going to test you on that. Okay. Now, what we could do is similar to what I was demonstrating. Actually, let's get back to that sample size 20 again. So what we could do is similar to what I was demonstrating to you before when we had that contour plot. Where would my sample fall? So this is exactly the same contour plot that we originally started off with. I put another contour there at 0.001. Okay, so you're way out there on that distribution. And then if I want to actually plot then the data on top of that, so add a layer to the plot, I can simply use the points function to do that, where I take the first column of x, which would be x1, take the second column of x, which would be x2, put that on the y-axis. Color of points red, LWD stands for it's line width, but it will give me the width of the point as well. And let's take a look at the plot. And we sort of got what I talked about. Yeah, we don't have anything inside that smaller circle there, that small circle there. Sorry, I'm not perfect. But it's just for this sample, it just doesn't happen that we have anything really, really, really close to the mean. But let's jack up the sample size. Let's go up to 2,000 and do exactly the same thing. Let's see what happens. And indeed, we get something that we would expect. A densely set of points towards the middle, and as we go out, the points become less dense because the probability of observing something outside of there is less. Okay? So let's say that I wanted to simulate data from a trivariate normal distribution. So in other words, p equal 3. What would I need to change here? I don't anticipate this will be a difficult question, but what do you think I would need to change there? How about for the mu vector?
3 by 3?
Well, we were 3 by 1. I mean, a length of 3, because this is a vector in terms of ours terminology. So I would just simply, add, let's say maybe I want a mean of 21 for x3. What would I need to do for then the covariance matrix? Make it 3 by 3. Okay, that's all. And so you can play around with this on your own to help you learn this material by maybe look at a p equal 5 case with a multivariate normal. See if you can simulate the data. Look at different sample sizes. So why is it useful to be able to simulate data? This is maybe a tough, I would anticipate this would be a tough question for you. Does anyone want to venture a guess? Extra credit if you get it right. So why does one want to be able to simulate data? I'm going to give you 2 reasons. The first deals with research. Let's say research from a statistician's point of view. So what statisticians do for statistical research, like those in a department of statistics at a research university, what you will do is maybe develop a new statistical method. And you want to know, does the statistical method actually work? So what you will do then is let's simulate some data under a particular situation where I know what the answer is. Maybe I know what the multivariate normal distribution is. And if I know what the answer is, I can try out the statistical method and see if it works. Okay? So examples of what works could mean is, let's say my statistical method is a new 95% confidence interval. Well, I could simulate, let's say, 1,000 sets of observations, calculate the interval every single time, and I want to check to see if it's a 95% interval, do 95% of the intervals actually contain the parameter I'm trying to do a confidence interval for? That's what statistics research often means. Now, in a non-statistical research context, you might have a situation where, okay, you're going to try to apply a statistical method to something. Maybe it's a new one that you haven't done before. And what you might want to do is test it out on a situation where you know what the answer should be, rather before you test it out and apply it to some real data. And so then you can see, does the statistical method give you what you expect? Okay, so those are the contexts. Both statisticians and non-statisticians can gain from that. So some statistical methods that we will look at in this particular class, is that me or somebody else? That's okay. Whoever it is, it's fine. I just didn't want to be accidentally hitting something on my keyboard. Now, some of the statistical methods that we have in this class have underlying assumptions about them, such as I assume the data comes from a multivariate normal a population characterized by a multivariate normal distribution. You know, in your first stat course, you often ran into particular situations. Let's say if you did a t-test. Now, that t-test statistic assumes that you have an underlying univariate distribution for everything to work as expected. Fortunately, though, if you have a large enough sample size, the central limit theorem kicks in. And even if you don't have a normal distribution, that t-test is still going to work as expected. Well, in this class, there will be some methods will have a multivariate normal distribution assumption behind it for it to work. There will be some methods that don't, but some that do. And so you might be wondering, well, how could I check if indeed that assumption is satisfied? So in your first stat course, if you wanted to check some data had a univariate normal distribution, what would you do? Well, you would do a nice histogram like this. And we can see its mound shape, it's symmetric. You might have went even as far as, let's say, putting a curve on top of it that looks like a normal distribution. You could be even fancier and put an actual normal distribution on it, draw everything to scale. That's how you would check. Do you have a normal distribution? Or is the normal distribution assumption satisfied? I should say it that way. Well, what about a multivariate normal? Well, unfortunately, it becomes quite difficult. Now, if we had, let's say if I wanted to check to see if a bivariate normal distribution assumption for two variables was satisfied, what do you think I could do? What would be the extension of what I just did here? Do a three-dimensional histogram. We're going to do something like that coming up. But that works okay for p equal 2. But what about p equal 3, p equal 4, p equal 5, and so on? Well, what's often done then in practice is this. Do a scatter plot of your data. Let's say here's x1 and x2. And if it looks like the points follow kind of within an ellipse like what we saw, okay, for x1 and x2, a normal distribution between just those two variables seems to be satisfied. Then what you would do also for, let's say, x1 and x3, do a similar type of plot. See if it kind of follows the ellipse pattern. Do the same thing for x2 and x3. Do that for all pairwise combinations of variables. And do this. This is what's called doing what's often referred to as a side-by-side scatter plot or a pairwise scatter plot, where you would do it for all possible combinations. You might have done this in another class. We'll look how to do it as well once we get to the graphics section. But I want to focus more on this idea of kind of a 3D histogram so that we can see what happens. So we're going to start with this normal distribution that we've been using before. And let's see here. And so we have a general idea of the shape. Sorry, let me get to the right spot in my program. Okay, I obviously did something wrong. Give me a a moment, please. Oh, don't do this to me now. Okay. What am I doing wrong? Ah, that's the problem. I never changed that back. Okay. One more time. There we go. The whole purpose was just a reminder, this is what the surface looks like. And so what you can imagine now is, you could have some histogram bars extending up from the bottom here, reaching basically up to the top of the surface. Instead, what I'm going to do is what's called a density estimator. And you may or may not have seen this before. So let's say if I have a histogram that looks like this. Obviously, this isn't a normal distribution. You might want to kind of overlap some kind of density estimator over the top of that. Tries to best approximate the height of those bars. You can do that in 3 dimensions as well. And you are not responsible for understanding how a density estimator is actually calculated, just the application of it. And so if I come back down here, let's actually do a higher sample size. So we're going to do 2,000. Nope. Okay. So what this is, and I'll explain the code shortly, this is an estimate of the density in 3D. Notice how it does have a very similar shape to what we saw when I had a green actual probability distribution drawn here. Why is it similar in shape? Because n was 2,000. Now, I could actually overlap the corresponding true probability distribution by using the PRESP 3D function. Use exactly the way that we've done before, but add equal true. And so now we see an overlapping of it. And we can see how the things are similar to where they were. And so we can see like almost like a bleeding through of the gold that represents the density estimate. Now, how did I actually get the density estimate? Well, there's a function called KDE2D, and you just put in for your first argument your x1, second argument your x2, put that into an object called fx.hat. Note that this function comes from the mass function, which is automatically installed in R by default, but you do need to say library mass. So then using the perspective 3D function, I pull out an x, I pull out a y, which is actually x2 for us, and then for a z argument, I pull out a z. So if I just highlight that, you can see these are all my estimated f of x's. And notice I put a color of orange there. So that's how I got the plot. You can also do contour plots with this too. You can see that on your own. But the main point here is I show what it looks like for n equal 20. And it doesn't look as good as what we like. As my sample size gets larger and larger, we can see we get closer and closer to that green probability distribution. Okay. So the last thing that we're going to talk about today, we won't finish it, but I want to get it started. We're going to talk about standardizing data. In your Introduction to Stat course, you'll learn about an equation like this. using the notation that you would have in that course. Typically, this is the notation. X is a random variable. Mu is the mean of X. Sigma is the standard deviation of X. And you call the resulting quantity after you do the subtraction, division, you call the resulting quantity Z. Where would you see this? Well, typically when you did a standard normal distribution, this is where you typically first see this. Now, oftentimes, we would like to use a very similar equation with actual data. The reason being, even if we don't have a normal distribution, the reason being is because this basically gives us a unitless measurement. What I mean by that is, let's say X is measured in feet. Maybe it's measured in seconds. Maybe it's measured in gallons. Or maybe X is measured in some other quantity of unit of measurement, okay? In fact, we saw with the cereal data, we had sugar grams, we had fat grams, we had sodium in milligrams. Oftentimes, we would like to make comparisons between the variables, but if they're measured on different scales, those comparisons can be distorted. And so by creating this here, where we take each data value, subtract off its corresponding mean, divide by the square root of its estimated variance, we create a standardized value, which is now unitless. It's no longer feet. It's no longer gallons. Why? So let's say that X was measured in feet. That means that sigma hat sub jj will be feet squared. When I take the square root of it, then that disappears. And then when I take something that's measured in feet divided by something else that's measured in feet, the feet disappear. And now I have a unitless measurement. So that, let's say, relate this to your normal distribution days. Let's say that I get something like ZRJ is equal to -3. What would that tell you about that particular observation for that variable? Would that be expected? Would that be unusual? If we relate this to a normal distribution, that's a big if, it would be unusual. The probability of, related to a standard normal, that is, the probability of getting something that extreme would be very unlikely. If I have something like this, ZRJ equals 0, then it tells us, well, look at X is exactly equal to its mean. That seems like that would be a reasonable thing to have happen. That would not be unusual. So this is what's called standardized data. We're going to do this sometimes with all of our variables. An interesting side note, those administrators at this university have a number of what they call metrics on every single department. And what do? Since these metrics are sometimes on different scales, like maybe one metric is number of books published by your department. Another metric could be number of dollars of research dollars you're bringing in. Obviously different scales. But they want to somehow determine, what's maybe an unusual department, either good or bad, or an average department. What do? They convert it to a standardized data. Okay? In fact, that's what they're using to make budget cuts. Okay, so let me, I think we're right just at the end. I guess I'm on time. Office hours after this class. Monday, please be careful here. Remember, you do have a quiz that's due. Please take note of that. On Tuesday, we will finish this data distributions and correlation section. We will begin we may or may not begin the graphics section. I thought we might do that today, but unfortunately, no. We will spend a large portion of the class doing a test number 1 review. Then, of course, looking further ahead, next Thursday, we have the tests. Are there any questions? Yes?
Can you go back to the standardized data real fast?
Yep.
Is the equation supposed to say the square root of sigma squared? Because if you're doing the square root of sigma with the square root of sigma.
So you have to be very careful here. It's the notation that we use versus what you would have had, in another class. Sigma hat sub jj is actually the estimated variance. Okay, I know it's something that you have to get used to. That once you have more than one variable, it's just much more convenient to not put that little square there. Okay, so that's why the notation developed. Okay, that's all here for today.